All right, continuing on with chapter 2, and this is probably some of the hardest material that we'll face, and it can be a little confusing when we're talking about potentials and electric fields, and then we'll move on into potential differences. But I'll try to highlight the high points and try to reinforce those. Now, remember, we're going with this idea, let me just sort of recap this, that we're going with this idea that potential, which we call V, and we'll later measure that in volts. We measure in volts now, but we'll later use that in terms of voltages for circuits. But it is innately or essentially a measure of energy per charge. Energy per charge. So if a charge has a certain amount of potential, that's a way of describing what its energy is. All right? And then when we talk about potential difference, we'll be talking about the differences in energy between two particular points. And that will cause a charge to go across that difference in energy. Now let's consider this, this situation. I have an electric field. I have a positive plate here and a negative plate here. The positive plate is going to be high potential, and the negative plate will be low potential. Just the value of the potential is higher on the positive plate. And then I have a charge, a positive charge, that moves from position A to position B over here. Now, has the electric field done positive or negative work to this charge? Well, if we think about work, work is equal to force times displacement. The force due to the electric field is going to be in this direction, and our displacement is also in this direction. So since the force and the displacement are in the same direction, the work is, of course, positive. We saw that last semester when we were dealing with work and energy, and work is force times displacement. If they're in the same direction, it's positive. If they're in opposite directions, it's negative. Now, has the potential energy of the positive charge increased or decreased? All right, well, it's moving from a point where the force is very large over here to over here. So the potential energy of the charge, as it moves along this electric field, actually decreases. So I'm doing positive work on this object, but its potential energy has decreased. So what then has happened to that energy? If positive work has been done and the potential energy has decreased, then where has the energy gone? And the answer to that is that change in energy, the work, gives us a change in energy, and this changes the kinetic energy, which is 1/2 mv squared. So the quick answer is just say that, well, the quick and really the true answer is say that as this charge moves through this electric field, remember I have this electric field, I have this positive charge, it's going to speed up. So the velocity of this charge will increase. It will gain kinetic energy. All right, so if the charge has lost potential energy at point B, then its kinetic energy must have increased. Then we can calculate the charge's velocity at B fairly simply, because we know the potential that is changed, velocity at B, or rather we know it's we know the work that's being done. So the change in kinetic energy is equal to our 1/2 mv squared. Let's go back here. I didn't state this explicitly, but I just want to make sure that it's clear. I said that the work is equal to force times displacement. All right. So that work then is equal to our force, which based on our electric field is Q times E. And then we're calling our displacement delta x here. So my work is equal to Q times E times delta x. And so my change in kinetic energy, which is equal to the work, is also going to be equal to Q times E times delta x. So this provides a very valuable relationship in that if I have a charge moving through an electric field and it moves a certain distance, then I can very easily calculate what its velocity should be. So with that, let's try this example. I have a proton is released at x equal -2 centimeters in an electric field of 1,000 newtons per coulomb. What is its velocity at 8 centimeters? So I have this electric field. I have a proton, and it's released at x equal -2. And then it moves through a distance up to x equal 8 centimeters. So delta x then is equal to 8 centimeters minus -2 centimeters. That's 10 centimeters or 0.1 meters. So our change in x, delta x, is 0.1 meters. I know the mass of a proton. You might not know it right off, but it's on your equation sheet. It's a good number to know, sort of for everyday use. 1.67 times 10 to the minus 27. And I also know what is the charge of my proton. Remember, this is the same as the fundamental unit of charge. It's 1.6 times 10 to the minus 19 coulombs. So now I have everything I need in order to find the velocity. Because remember, I'm saying that my work is equal to my change in kinetic energy. And it's going to be QEX equals 1/2 mv squared. And I solve that for v. So however you want to do that, I'll just solve it algebraically first. And it's going to be the square root of 2QEX divided by m. We're going to put some numbers in there. What was our electric? Oh, it was 1,000 newtons per coulomb. X was 0.1 meters divided by my mass, which is 1.67 times 10 minus 27 kilograms. And that'll give us our velocity. I get a velocity of about 140,000 meters per second. So, or let's see, that's 1.4 times 10 to the 5th meters per second. That's a very valuable tool for us to have. Now let's look at, let's see, I thought I had a quick test question here. I'm going to pause this for just a moment, pick up later.